So this is probably the only talk on photons, basically looking at topological physics in photonic systems. So I'll review a little bit what we have been doing in the past few years, and then some new results. So the outline of the talk is the following. I'll show you and review the topological ring resonators, basically how we can engineer band structures that have topological features in photonic system. Then how we can measure topological invariance, in particular how we can measure winding number in a photonic system. So this part is completely linear optics. It's non-interacting physics or single particle physics, whatever you want to call it. Then we move to the quantum direction, looking at, in particular, how we can look at quantum optical properties of the topological system. Is it any use to use topological property in looking at quantum properties of light? Whether, for example, we have quantum transport properties that are now robust. Can we have entangled state that can be propagated in a robust fashion, etc.? Can we generate single photons in a robust way? And then I'll switch gears and then talk about electronic quantum Hall systems and use photons to probe and manipulate them. So this part is more experimental. The last part is purely theory. Okay. So quantum optical, magneto-optical properties in the optical domain are very weak. So when you put a magnetic field, photons don't feel it. So if we want to tell photon to feel a magnetic field, very similar to a single electron on a square lattice, we have to fake it for the photons. In particular, if I have a two-dimensional array of ring resonators, these are ring resonators, so electromagnetic waves are confined at the rim of these circles or ovals. If a photon finishes a plaquette like this, it should acquire a 2 pi alpha phase. If it goes in the counterclockwise or in the clockwise, it should get the opposite phase. Okay? So more formally, we should have a Hamiltonian like this, which is basically a single particle hopping on a square lattice in the presence of a uniform perpendicular magnetic field. So this is basically the Hofstadter model. Okay? So in order to do this, it turned out that one can use a very simple trick. We have two resonators that are resonant with each other. Lambda is the resonant wavelength of light, m is an integer, and we couple them with a resonator that is anti-resonant with these two. In particular, its length is m lambda plus lambda over 2. So if a photon goes around here and then acquires a 2 pi m phase, it would acquire a 2 pi m plus pi over 2 phase if it goes around the bigger loop. So the consequence of that is very simple, is that if a photon is circulating over here, reaches this coupling region, it comes here, it goes around, and then it comes here. It would like to go back and continues complete the loop, but it's anti-resonant, so it won't do it. Instead, it would go to the other resonator. It will circulate a little bit, and then it goes back. It goes back now from the lower arm. So when I go from left to right, I take the upper arm. When I go from right to left, I take the lower arm. If the optical paths are not the same, the accumulated phase will be different. So in particular, the phase to hop forward and backward are not equal to each other. In particular, they're exactly opposite to each other. Okay, so that's how we engineer this non-symmetric phase for hopping. And now if we arrange this resonator such that we have this phase as a function of the number of row, we can introduce a magnetic field in the Landau gauge. So the experimental setup actually to do this is uses silicon and insulator technology. So these are our ring resonators on the SEM image. So this is a ring resonator, this is a connecting resonator, this is another ring resonator, etc. Then when it goes around the plaquette, it gets this 2 pi alpha phase. These resonators are not perfect, they leak light, and the leakage of the light is proportional to the amount of light that we had on each resonator. So if we put a microscope and then look at this resonator, you basically are measuring the amplitude of the wave function at each point, just the magnitude. So if we have if we fix alpha, so this is Hofstadter butterfly. I'm sure everyone knows about this. This is the alpha that characterizes the magnetic field, and this is the energy of the eigenstates of the system. So we fixed alpha at this point. So we are looking at these eigenstates. Now, if I send a photon that is resonant with one of these states, it will go into the system. If the photon is not resonant with any of these eigenstates, it will get out of the system. This is in contrast to the electronic system. Electronic system, you park the Fermi level over here, and then you fill up all the levels over here. In a photonic system, you always interrogate a single frequency. And as long as you don't have any elastic scattering, you should not worry about other states. So if now we inject, so this is transmission as a function of frequency, and if I inject now a photon that is resonant with this band, this is one band that the photon goes around, comes here, it goes around this edge, and it comes out, and this is the other band, which corresponds to the photon going around this edge, and then coming out like here. So a while ago we saw that in the experiment that one can match it very nicely with the simulation. The photon comes here, goes around the edge, comes out, experiment the same, and also for the other edge, the photon goes in, comes out, goes in, comes out. More aggressively, we can actually remove one of these resonators, and then what you expect is that the photon comes in, it would like to backscatter, but the other state is of resonance, the state that goes in the opposite direction. So instead it would go around the resonator and continues the way, and this is what you see in the simulation, and that's what we saw in the experiment. Okay. So this is one system, TOPS one photonic system that we looked at. There are many actually interesting other photonic systems that people are investigating to implement a synthetic gauge field in different frequency domains. R was in the telecom domain, 1.5 micron. But one can do it in the optical domain, in the microwave domain as well. And there is a nice review, up to that point on the progress. Okay. So that was the imaging of the edge states. One can also look at the transport property. One can look at the system, and then continue and then repeat the experiment for different samples. This is transmission as a function of frequency. Each line, each color is for a different sample. So each sample has a different disorder realization. So from one sample to another sample, you have a different realization. Now, if we superpose all the spectra on top of each other, you see that the transmission in the bulk is very noisy. From one sample to the other sample, you see that the transmission changes a lot. But in the edge state, you see that it's robust. In particular, the Wigner delay time, the time that takes for the photon to go from one side to the other side of the sample, as a function of frequency, is very noisy for the bulk, but it's very robust for the edge. Okay. And then one can also look at the scaling of the system. This is transmission as a function of the system size. Here is the number of resonators involved. You see both of them exponentially goes down because of the loss. There is always loss in the system. But when we compare one-dimensional system, just one-dimensional array of ring resonators, well, one-dimensional array of ring resonators, and a two-dimensional array of ring resonators with this synthetic gauge field, we see that the two-dimension outperforms the one-dimension, and the reason is in the one-dimension we are not only the transmission is not only inhibited by the loss, but by also Anderson localization. Because these resonators, when we fabricate them, they're not exactly perfect. So when the photon hops, it will go back and forth, and eventually it would get localized in the system. So this is kind of the precursor of the Anderson localization. If it goes higher and higher, it should stop at some point. But now, in the 2D system, it's just the loss that is inducing this exponential decay. Okay, any question up to this point? It's kind of the review of some from the old works. So now, with measuring the topological invariance, how we measure the topological invariance in this photonic system, but in particular, what is the integer conductance in this system? There is no conductance. We just look at the transmission in photonic system. So what is quantized? You go back to the Laughlin's argument. We start with just a ring. If you have a ring and you apply a magnetic field into it, then the band structure is like this. So I have a tight binding model, and I have a bunch of states. And if I change this complex hopping, then these states start to flow. The clockwise will flow in one way. The counterclockwise modes will flow in the opposite way. Okay, so if I just have a ring, I'll see some of the states going up, some of the states are coming down. So what Laughlin did was that actually now let's look at the same system but in an annulus. Now the forward-going states and backward-going states are separated in space because of the presence of magnetic field. So now when we look at the spectrum of the system, so this is energy, this is the momentum of these states at the edge. When we induce this phi, some of the states will flow upwards, some of the states will flow backwards, but they're spatially separated. So now if we put two waveguides at the edge of the system, we can see the flow, the spectral flow of these states. In particular, for these blue states, we see that we have, like, say, 5 states. And when we change the phi from 0 to 2 pi, they would flow in this direction. Once we come back to 2 pi, the spectrum should be exactly the same because of the gauge invariance, right?
So is different fluxes, different samples, or can you tune it in one sample?
I'll tell about this. But this is just the idea. So if I look at the transmission as a function of frequency, I have a magnetic band over here and another magnetic band over here, and these are the edge states. Now, for phi 0, we have, like, say, 4 peaks, and now when we change phi from 0 to 2 pi, they will move and then replace each other. So how many times they move is basically the winding number of the edge state, and how many modes we have over here. So in the experimental realization, we have the following situation. We have an annulus, and it turned out that actually annulus, for various reasons, was not the best topology. But how we apply this extra flux in the system is very simple. We just add heaters. So if there are these ring resonators, we add a heater that changes locally the index of refraction, such that when the photon hops from here to here, it not only gets that 2 pi alpha phase, the uniform magnetic field that we had engineered in the system, but also that tunable phase. So if we apply that, it's as if we have applied a flux of theta only at the edge of the system. If I do it for a branch cut, then it's as if we have pierced the system with a magnetic flux in the hole. So now let's look at the spectrum of the system. This is measurement, this is simulation, and then we apply that extra gauge field. So the y-axis is the magnitude of this flux from 0 to 2 pi. The contrast is the transmission, and the x-axis is the frequency. So when we change phi from 0 to 2 pi, we see that some of the states will flow in this direction, some of them will flow in the opposite direction. In particular, if we zoom in, we see that these states will flow, and then and compass back to the same place. So here I had a high intensity, now here I have the high intensity, so the system will come back to itself, but it has crossed this perpendicular line once. If it had crossed twice, then the winding number would have been 2. So this is a direct measurement of the winding number. Is that okay? Yeah. So that was, again, as I said, completely linear. Now we see what are the potential quantum directions that we can take. So there are 2 categories. I would like to think like that. There is one that it's a linear or weakly nonlinear system. The other one is a strongly interacting system, that the interaction between photons is mediated by some dipole in a very strong way. So in the linear system, we can look at the quantum transport of non-classical light. In particular, we can take the same system that was linear, but we send non-classical light into our port. So if I take a 2-photon state, which can be written like this, so a creation of a photon at position x1 in the waveguide and x2 in the waveguide, the wave function should be symmetric. It's the bosonic wave function at some snapshot time t. And then this photon will go into the system and comes out. Depending on the central frequency of this 2-photon wave function, it can either go through the edge. So if it goes through the edge, it's a chiral edge. It should come back. It should come out the same way. So this is the amplitude of the 2-photon wave function. It goes here and it comes out the same way. But then if the central frequency is in the bulk, then the 2 photons will go here, and then one of them can surpass the other one. They can interfere. They can come out. So depending on where we send it in the bulk, the same state, different outputs are expected. So these are all simulation. We don't have any experimental data yet. The other thing that we are looking at is the topologically robust generation and amplification of photons. So this is in line of what Gil was actually talking this just before. And we use this topological robustness in the system. So we look at topological robustness of photons. Let's assume that we have our system, and the system repeats itself after each free spectral range. Meaning that you can look at, these are resonators that have a mode number 100, it can wind 100 times, 200 times, 200 plus 1. So these are different, basically different modes of the system. This is M100, M101, 102, etc. And the physics repeats itself. So the band structure that we had, it repeats itself. Now, if we pump at one of these bands, then we generate photons in the upper and in the lower mode. In particular, it's called the signal and idler. So if you send the photon through some Chi-3 process, you send 2 photons at this frequency, and it splits into two photons in the other band. So this is how people, for example, generate pairs of photons, either off-chip or on-chip. And there is a big interest to make these things actually on-chip in a robust way. In particular, have a very nice 2 photon states that are separable. What separable means that if I look at the spectral, joint spectral density of these 2 photons, let's call this omega 1 and omega 2, and I plot omega 1 versus omega 2, it should look like a circle. If it's not a circle, it means that they're entangled, and we don't like entangled photons as a single source of photons. So if we now take a one-dimensional system, we take one ring to make these single photon pairs. If you want to increase the yield, you want to increase the number of rings. So you want to have like 10 rings, 20 rings, etc. But as we said, they're not exactly the same when we nanofabricate them. So when you look at this spectral function, you see that you have resonances in different places. These are different samples. So once we are glowing like here, it's like a square. Here we have some dots. Here we have, these are all due to that disorder that I mentioned. But when we do it in a 2D topological system, then we see a robustness. This goes back to the slide that I showed about the robustness in transmission and the delay time. Here, it's actually more sensitive because it's related to the t squared, the time squared in that. So that was kind of the weekly nonlinear part. Am I doing with time, Anatoly? 15 minutes, okay. So now for the strongly interacting one, this were like still experiments, but now here it's purely theory. So the recipe to get fractional quantum Hall states is that we should have a gauge field, we should have some interaction, and then we get fractional quantum Hall states. Very similar actually to the atomic systems, that we have some lattice with some gauge field, and we have a strong on-site interaction. So for photons, this on-site interaction is basically the kernel linearity. Is when a photon sees the presence of another photon. And it should be so strong that the single photon should block the transmission of the other photon. That's what it's called photon blockade regime. So when U becomes comparable with J. And that's actually not easy to achieve, but there are many experimental efforts around the world from optical frequency to microwave to achieve that limit in a scalable way. For example, microwave domain, they use Josephson junction to induce that strong nonlinearity. In the optical domain, one can use Rydberg atoms. And I'm not getting actually to how engineer that. It's a big challenge, and I don't want to undermine the difficulty of it. But I would like to point out what are the theoretical problems already over there. So let's focus more on this Hamiltonian. So this Hamiltonian, if alpha is small, for fixed filling factor, in particular if the filling factor, the number of photons divided by the number of magnetic flux is fixed, it's if it's 1/2, then the ground state is given by the Laughlin state. So Z is the complex position of the photon in the two-dimensional system, and then you see that it's an entangled state. And for this particular short-range interaction, and this filling factor, it's gapped. So it's exact ground state and it's also gapped. But how can we make this photon number fixed in the system, and then how we combat loss? Because imagine that you have that fixed photon Fock state, like 100 photon Fock state, but if you lose one of them, then the whole system is dead. So one way that we thought about with Elliott Copied and Steve Simon was to use the incompressibility of the system itself. So the compressibility means that the cost of adding a particle to the system is not the same as the cost of subtracting a particle from the system. So for a single site, this means that the cost of the energy difference between 0 to 1 is different from 1 to 2, basically a nonlinear harmonic oscillator. So now the question is how you can stabilize the system at 1 photon Fock state. Okay? So the immediate guess is that, well, we can come with some laser that is resonant with this 0-1 frequency and not with 1-2, and then we can populate 1. But that's wrong, because if you shine a laser at this frequency, you at very strong intensity, you get a superposition of 0 and 1, half-half, not 1. How should we do that then? So the idea we had is the following. We have an ancillary spin, or it can be actually a harmonic oscillator as well. And then we couple them in this anharmonic, in this parametric fashion. So we have a flop-flop situation that we drive the system with the sum of this and this transition, such that when the drive is on, from this ground states we go to the upper states. And then since this gamma is very large, we engineer it to be large, then this will come out. Again, this parametric coupler would like to take this over here and then take this over here, but there is an energy cost delta. So since that there is that energy cost, it cannot go up and it would stuck over here. If we lose a photon, the parametric coupler again puts it back. So we stabilize it in the steady state. So now we can generalize this to the many-body case. In particular, for this fractional quantum Hall state that we mentioned, if we have a flat band, if we have this next nearest neighbor added to the system, it's almost flat band. So we can add these photons one by one until we hit the Laughlin state. This is the number of photons. This is the energy. And then once we hit the Laughlin state, we cannot add the extra particle. So we stuck over here. If you lose a photon, you create two quasi-holes, two half photon. Then you pump it back, you stabilize over here. So it would be a steady state. It's not a pure state, but its majority is a quantum Hall state.
Does that depend on the ratio between the decay of the spin and the pumping? Purity of the one photon?
So one has to optimize all those parameters. So one has to optimize these parameters. In particular, omega and gamma s should be about the same order, and larger delta and smaller gamma over here is better. So these are given by my system, and then I optimize omega and gamma. So there are other proposals that we looked into, and to be honest, it's not clear which one is better for which system, but we're exploring different ideas, what is the best way to go about this. I would like to mention something as well before moving on to the other topic, is that in this photonic system, sometimes one has the opportunity to engineer some more exotic Hamiltonian. In particular, there is this old paper by this gentleman that they assume that if we have this parent Hamiltonian, this three-body interaction, then for nu equals 1, we could get a Pfaffian state in the ground state and gapped. So the lattice version of it is basically means that we should have this tunneling, but then is three-body interaction at one site. So if you look at this interaction, is nothing but the following. So a U2 interaction, a two-body interaction, means that 0, 1 is one energy, and then 1 to 2 is a different energy. So this is our usual two-body nonlinear situation. A three-body interaction means that I can have 0, 1, and 2, and the cost of going from 0 to 1 and 1 to 2 is omega. But if I want to go from 2 to 3, there is a cost. So if you take actually a qubit, in particular a fluxonium, and you tune the washboard potential such that the washboard potential allows to 3 bound states like this, and the third one is very far, then you have effectively made a 3-body interaction. So that was again a proposal that hopefully it could be done in the microwave domain. Another avenue that one could explore is also this chiral quantum optics. There is a dogma there was a dogma in quantum optics that if you have an emitter and you couple light to it, it can couple both to forward and backward in the same way. But it turns out that one can engineer it so that it would go to only in this way and not the opposite way for an engineered waveguide. So one of the things that we are exploring is that what if this waveguide is actually a topological edge state? So we make our system such that we have an edge state that it's helical, and then we couple some solid state emitter, and we would like to see how the photon is coupled to these edge states. In order to do that, we cannot use our ring resonators because once we introduce the emitter, we break this chirality in the symmetry. We move to another architecture using photonic crystals where they are more compatible with the solid state emitter integration. In particular, we take a honeycomb lattice and we deform it in 2 different ways. We deform it like this, we squeeze them like this, or we expand them like this, and we introduce a gap. But then if you look at it carefully, one can actually write a simple tight binding model to it and then solve it. Depending on the ratio of T1 and T2, one can open a band gap in different directions. So Martin actually talked about this JQI model. This is exactly this JQI model, but 2 copies of it now in 2D. Depending on this T1 and T2, you open a band gap and then invert the band, very similar to the electronic system. So that's what we are doing here. We have an emitter. We have 2 systems that have 2 different topologically distinct character. So the band is inverted across this region. And then we get a topologically robust edge state. And now if we excite it with sigma plus, it will go this way. If it's sigma minus, it will go in the opposite. So it's basically a helical edge state. And that's our system so far. 2 nights ago, student Sabyasachi actually got some results after a year and a half, but it's very preliminary, so I don't show it. But we are very excited after a while that we got these results. So I'll summarize up to here and then use the, you're standing up? Yeah. So yeah, because I calculated, because there is one part of the pathak that's not there. So this is all photonic systems and all the collaboration I mentioned in the talk. So now photons and quantum Hall states, and these are these gentlemen that are leading the project, in particular Tobias. You can see it. He was somewhere. It's here. Yeah, he was here. Yeah. So what is the situation here? Can we use light to detect and manipulate electronic topological edge state? So this is the schematic of the system. We have a 2-dimensional system, and we have a strong magnetic field, and we would like to see whether light can probe and manipulate these states. So this is a result. This is an experimental result from Grenoble. There is a graphene in the presence of magnetic field. You have Landau levels, and the Landau levels are not equidistant in contrast to a quadratic Hamiltonian. They are actually non-linear. There is a square root n dependence on them. So one can actually easily see it in this situation. So in a quadratic Hamiltonian, you start with P, and then you do minimal coupling. And then when you diagonalize it, you introduce the ladder operator, you get A dagger A. In the linear case, you start, for example, for graphene, you start with this, you do minimal coupling, and then instead of A squared, you get A. So now you have to square your Hamiltonian to get, again, A squared A. So now the energy states will depend on square root n. So this square root n is important, because if one of them has a dipole transition, then it cannot go to the other transition. So for example, if I go from 0 to 1, I cannot go from 1 to 2 with the same frequency. So if you come with a specific laser frequency, you can address a specific transition and isolate that specific transition, which is nice. So now what they looked at this optical transition and then see the optical. So these are different Landau levels and Landau level transitions that one can resolve optically in the terahertz regime. So what we looked at, we said that, okay, if we do this in the optical domain so that we have some spatial resolution, then one might be able to map the disorder in the system. So imagine that we put the Fermi level between these two Landau levels. So now a photon comes, it will excite the atom, the electron over here, it will recombine, and then if we spectrally and spatially resolve these resonances, then we can map out the disorder landscape. In particular, this is a simulation that Michael did. So that we have a disorder that is randomly generated, and this is the reconstructed one by just looking at the optical emission. But one can, if we look a bit closer, there are actually even more interesting things. In most cases in quantum optics, we look at the dipole approximation. The system is smaller than the wavelength of light. But if the system size, if the wave packet, if the electronic wave packet is larger than lambda, then we can have multiple emissions. And we claim that actually in quantum Hall systems, since some of these states are extended, one might be able to see multiple emission in these systems. In particular, if I look at the transition between two different Landau levels, so this is 0 Landau level, 1 Landau level, in the symmetric gauge, this M characterizes the angular momentum. So these are Z to the M states, and this is again Z to the M states. Now, if I look at the light coupling, basically P dot A coupling, then this A, if we write it in the cylindrical coordinates, we see that it has also an azimuthal component to it. It's e to the I L theta. And then you immediately see that we get some selection rule. And then the rest of it will be some spatial overlap. And this is non-zero, basically. In a usual case, when this is small, it exponentially goes down as a function of L. But in this situation, it does not actually go as a function of L. It is flat. So more specifically, if we now look at this graphene, and at the edge, or because of some disorder, the band is curved. Now, if we excite one electron over here, it can come down, or it can come down from here to here, here to here, here to here. The difference between M of the excited state and the ground state, which characterizes the canonical angular momentum, should be dumped over the photon that is exiting the system. So if the system size is small, if my graphene sample is very small, then if I look at the branching ratio as a function of magnetic, as a function of the orbital angular momentum order, it exponentially goes down. But then if the system size is large, so that these orbits are very large, then you can actually dump a non-zero orbital angular momentum, and at some point it goes to zero. The reason it goes to zero is that the higher orbital angular momentum you go, the corresponding optical mode, its hole gets bigger. So as I said, these are Bessel functions. The Bessel function has a hole inside, and you make the order of the Bessel function larger and larger. At some point, it becomes bigger than your sample. So then, of course, you're not going to couple to that light mode. So that's basically the reason that we have this sharp fall-off. So I say something and I finish. How much? 2 minutes? Oh, good. Okay, so now that was like looking at the integer quantum Hall effect. Now let's be a little bit more aggressive and see whether we can even manipulate a fractional quantum Hall effect. Let's assume that we have two Landau levels, 0 and 1. So this is a work that was done by Puang Aimi and Ara Ghazarian and Michael Gullens. So imagine that you have a two-level system, two Landau level, optically couple them, and then now this optical coupling couples two different Landau levels. Now the question is that whether different Landau levels play the role of two layers. So in bilayer magnetic, bilayer quantum Hall effect, you have two physical layers. Here we have only one layer, but we optically couple two Landau levels so that the optical field that's coupling them play the role of the tunneling, and then the different Landau level play the role of the layers. So if we go to the rotating frame, then basically these two states are now quasi-degenerate, and many of the interaction terms that were not relevant now becomes relevant, because usually you ignore Landau mixing in all these states, which you should not do in graphene, but we usually do. But now here we cannot really do, because you can really scatter from one of these states to the other states easily, because of we are in this rotating frame. So what kind of state that we can engineer? So we looked at the two-third filling, which is one of the least controversial ones, but you can ask Tobias, and he will say it is actually controversial. But so just looking at this, you can see now we can look at the energy spectrum. So this is energy as a function of the strength of that coupling. So in 0, 1, we don't see much thing. We basically see that we have a very large overlap with Laughlin state, but with a dressed Laughlin state. So what I call dressed Laughlin state is that we have these two Landau levels, and now we couple them. So this would have a little bit of mixture with this one, and this have a little mixture of upstairs. And now, since that mixture is smaller than E squared over LB, then we make a Jastrow factor between these guys. So we make a Laughlin state out of those dressed Landau orbitals. So basically, we make now, usually from Laughlin argument was that we go from here to here by making Jastrow factor within a Landau level. Now we have to make a Jastrow factor from these dressed Laughlin state. And when you see a very nice overlap with the dressed Laughlin state. And if you look at the polarization in the system, you see that it's very polarized. So it's polarized in one of these dressed states. But if you look at the other state from 1, 2 transition, then we see something opposite. We see that the polarization actually becomes 0 when omega is smaller for this transition. And then it is basically a singlet state. So we are actually looking at different problems that now arises in the system. One immediate question is that whether we thermalize in this driven system. If we have a driven system and we are this in rotating frame and we are doing a numerical simulation to look at the ground state, is it a legitimate way to look at the system? We think it is, and we think actually this phonon electron-phonon interaction could provide that thermalization, but it's still an ongoing work. Other idea is that whether we can engineer some Haldane pseudopotential in this system now that we have access to the orbital angular momentum. Can we construct these twist effects, etc. So with that, I would like to thank all the collaborators that I mentioned in the talk and you for your attention. Thank you very much.